Please let me know when we should begin.
Yes, sir. Yes.
It's about time.
Yes, sir. We'll start.
So let me know when to begin when everybody's ready.
Sir, can you hear us?
Yes, I can.
Can you open?
Yeah, Ramesh, the main mic is still on mute, I think. It's loud. Hello, Anil.
Sorry. Hello.
Hello.
Hello, sir. Are you? Can you
Yes.
hear me?
Yes, Arvinda, I can hear you.
Shall we start?
Yes. So if everything is ready, then it's wonderful to have Professor Anil Prabhakar with us. So Arvinda, we are starting, right?
Yes, we are starting.
Excellent. So good afternoon, everybody. This series of seminars is turning out to be very exciting. And in continuation of the discussion on quantum internets that we had on Saturday, Professor Shaikat Goha gave a very exciting talk. Today we have a brilliant contributor to this field from IIT Madras, my young colleague, Professor Anil Prabhakar, who has contributed richly to the field of the quantum internet. So we're very proud and privileged to have Anil with us. Anil, a very hearty welcome to you. And may I request Professor Arvinda to please introduce Professor Anil Prabhakar. Arvinda?
Yeah, thank you, sir. Welcome, Professor. So it gives me a great pleasure to introduce Professor Anil Prabhakar. And he has been with the faculty of Department of Electrical Engineering, IIT Madras since 2002, and is engaged across multiple laboratories that work on quantum technologies, fiber lasers, and optofluidics. He is a member of the scientific management board for LIGO India to detect gravity waves and the Indian-based Neutrino Observatory. He currently serves on the editorial boards for scientific reports, IEEE Transaction Magnetics, Journal of Magnetism, and Magnetic Materials. He has various academic responsibilities, which includes chair for BIS panel on quantum computing, and Indian representative at IUPAC 69 panel on magnetism. And he is a member of Joint Technical Advisory Group of the Empower Technology Group, Office of Principal Scientific Advisor to Government of India. And he is in the Scientific Management Board of LIGO India, and as a member of UGC Expert Committee to frame guidelines for equitable access to quality education and SDGs. And his current research interest in the areas of quantum technology have applications in metrology, quantum communication, and quantum computing. As a co-founder of QNew Labs and of QFluence, both incubated by IIT Madras, he focused on quantum communications and photonic quantum computing, respectively. An earlier startup, Unilumen Photonics, that focused on fiber lasers, was acquired by Jiva Sciences. He is currently the director of Yeli Mobility and Enability Foundation, companies that focus on rehabilitation engineering. He has many research publications and has co-authored a book on spinwaves, a few book chapters, and has 18 patents and wide range of devices in the area of photonics and magnomics and assistive devices. It really gives me a great pleasure to welcome you, Professor, for this talk.
Thank you, Arindam. That was a long introduction. I sometimes surprise myself when people read all of that out. There must be some way of my changing the slides without walking back and forth. Is there a way to change slides without my walking back and forth, or do I go there and change slides? Do I change slides from there? Yeah. Okay. So then I should be standing here, right? Oh, there is something down. All right. In the meantime, can you just go back to my first slide? Yeah. So the title of the talk is Quantum Internet with Local Access, and I thank you all for being here. I hate talking to an empty room. As you can see, I chose the title to go with an acronym. It's called KILA. And you'll see why I call it KILA. I start with this, and I'm also going to end with it. In the middle, you'll hear other things, right? I represent the Center for Quantum Information, Communication, and Computing, which also has this nice acronym called CQUIC. Right? So life is all about acronyms. You get it right. Okay. So I'll give you a brief introduction. I'll tell you about my motivation for metro area quantum access networks. And then we'll talk a little bit about quantum key distribution and how this goes. Any points for guessing what the acronym for metro area quantum access networks is? It's MACAN, right? So you have MACAN and then you have KILA, right? So you have a house and you have a fort. And it's all about security for us. And that is where we talk about quantum key distribution. Go ahead. Right? The center itself does a lot of work around photonics. We do, of course, do quantum networks, which is what we're going to talk about today. We also do quantum computing or quantum inspired computing, and we do quantum information, right? And all of these things tie down together when we start building systems. The faculty of the center, as you can see, there are many. There is Siddharth, who's here today, works on devices. We do systems. We have people working on quantum computing, doing both information theory simulations and applications, as well as in quantum communication, right? So it's a large team. These are just the faculty. If you think of the number of students under each faculty, I mean, there are a lot of people, right? The technology platforms are also interesting now. Traditionally, we've been working on sort of nonlinear devices, TRL4 for quantum communications. But we've also began working on silicon photonics. And now we're going to start having some of our photonic integrated chips out. It's very nascent work on diamond photonics. So all those things are actually quite relevant to what we're talking about today, right? What I'm not talking about today are the qubits on the cloud, which is also at technology readiness level 4 and above. That's where we actually test some of our ideas that we use on our quantum systems. Okay, so why are we interested in this idea of a quantum internet? It actually comes down to this fact that there's a quantum computing race going on. And this race is driven by a number of well-established companies. The ones in green are color-coded to tell you what technology they're working on. The ones in red, well, I guess this ion trap should have been red and not brown. And the ones in black are the ones that do photonics. There's also Microsoft that is trying to topological insulators, and Intel that's promising us spin qubits. And there is a separate entire argument that talks about doing circuits versus annealers in quantum computing. Why is this relevant to us at all? Sorry, please give me a second while we figure out. Yes. Perfect. Why is this relevant at all to us? Is because these quantum computers are now becoming a reality. I just realized I have to update this slide. IIT is now pushing 84 qubits. IBM is pushing 400 qubits. Google with its Bristlecone chip is at 72 qubits. D-Wave has 5,000 qubits, but it's an annealer, and Honeywell has 150 qubits, but it's ion traps. These are all what are called noisy intermediate scale quantum devices. And these devices are slowly coming mainstream. You can today purchase a Rigetti machine of 80 qubits. You can access IBM's 400 qubits online. D-Wave is also available online. Honeywell is available online. So all of these are available for access, and you can even purchase some of these systems. These systems are unique in the sense that you can do different types of things with it. Circuit-based systems rely on both entanglement and superposition, whereas annealers rely mainly on superposition. They don't do entanglement. And they're unique hardware to solve some hard problems. And what are the most common hard problems that we can think of? Well, there are two hard problems that are written here. One is uses an algorithm called Grover search, and the other one that uses Shor's factoring. Shor's factoring is the one that is of interest for us today. It is primarily related to this idea that if you have a number which is a product of two primes. So if I say 21, then you can say it is 7 into 3. If I say 121, you can say it's 11 into 11. But after a while, you can't do it mentally, you can do it on a computer. If I make it large enough, then you can't do it at all. And the idea is that with Shor's algorithm, you can do it. It reduces from a problem that was exponential to a problem that is polynomial if you use the algorithm. So if you have a certain size of a problem, you might be able to do it better on a quantum computer than on a classical computer. And this idea of factoring of numbers into primes is what we use for our digital security today. So all our passwords, all our UPI, everything, Aadhaar is all secured using these hard problems. And unfortunately, they all become insecure if you have a large enough computer. And the computers are coming. So the question is, what do we do about it, right? I usually like to put this particular slide up because it tells you when the computers are coming. You'll see this is from IBM. Earlier, we were stuck at 2765, 127 qubits, but you'll see that they have changed the technology. And now they're able to go up to 400 qubits, which we got earlier this year. Later this year, we will get 1,000 qubits, and then we'll get 10,000 qubits. They've changed the technology. They can now parallelize it. It is all going to come together. And there are a whole bunch of applications. The one that we're really interested in is in cryptography. That is why we are doing Kila, right? It's a fort. And we want to protect ourselves against people who may have these quantum computers. So the idea is that in about 2035, we can expect that we will have cracked all our passwords. So one could easily say that's 12 years away. I don't have to worry about it today. Right? Why is this guy giving a talk today and telling me about something that is not going to happen for 12 years? But as you'll see, the danger is today. It is not really 12 years away because someone could do an attack which is called save and decode later. So I could tap your communication channels today, save it. I save all the data. So it could be your own personal data, financial data, medical data. It could be of national security. And if I save it long enough, eventually the quantum computer will show up and then I can decrypt everything. And then we have another version of WikiLeaks, right? So that is the danger. And So although today we are in this region where we have this window of opportunity to do optimization and combinatorial logistics and QML, which is interesting, these are the same algorithms that we are using to decrypt the data that we have stored. So it's not like other people are the only people who are saving our data. We are also collecting data from places that our neighbors are leaking, and that data we are trying to decrypt on our quantum computers that we have access to today. So you can imagine that our neighbors are doing that to us, right? And we don't want to wait till this happens. We want to safeguard our data today. When is it actually going to become insecure? It's going to become insecure, we believe, by the time we have about 10,000 qubits. But you look at the map I had, the technology roadmap, you will have 10,000 qubits in a few years, right? You have 1,000 qubits this year, might have 4,000 next year, and the year after you will have 10,000. So you are very close to actually reaching this blue curve where you can have near-term applications in a few years' time. On noisy qubits, You see on the y-axis is the limiting error rate, right? Another way to ask the same question is, how many qubits do I need in order to correct for a noisy qubit? And that number could be, depending on who you talk to, it could be 50 or it could be 100, right? So if I needed to run Shor's algorithm with, say, 100 qubits, I then need 100 into 100 noisy qubits, which is 10,000. So it's a real danger. I mean, if there are people like me out there, they'll be pushing this envelope as far as you can in order to be able to do some of these things. The other question is, when will you know it actually happens? It's not that someone who knows how to crack your password is going to come and tell you, hey, I cracked your password. They're going to mine that for all the information that they can get before they tell you that it is, lost. In fact, there are known backdoors in some of our existing algorithms that people did not reveal until it was discovered. Right? So that is the state of the art, right? So we'll have 1,000 qubits this year. This is an example of what happens with public key cryptography. There are some algorithms that are definitely insecure. This is the one that we use, which is likely insecure. The only one that is information theoretically secure is this one-time pad, an OTP, right? AES is likely secure, but it's not provably secure. OTP is the only one that we know of that is provably secure. So how do we do this? We encrypt data. We take what is known as plain text. We encrypt data. We create ciphertext. We share it. We share a key with the second party Bob, who has the secret key, and he decrypts the data and recovers the plain text. What happens if there's an eavesdropper? And what happens if there's a malicious attacker, malware, right? These are all the ideas that cryptographers worry about. What we try to do in quantum key distribution is, I should have probably not this, is derive a common private key by a protocol. And I talk about factoring. Actually, what we use is another protocol called Diffie-Hellman that depends on a discrete log problem. It's of the same complexity as factorization. And usually the idea is if you can solve one problem, you can solve the other problem in a similar manner. Right? So this is the security assessment that before the advent of quantum computers, you had this kind of security available with these number of bits, right? The minute you have the quantum computer, the security levels goes down. So today you're using 256 bits, it will become 128 bits. Public key cryptography is likely to be all broken, right? And this is the danger. So what do? Is we yeah, so effectively your effective security is only 128 bits once I have a quantum computer. That's what it's trying to say. right? You think you have 256-bit security, but because I have a quantum computer, you actually have only 128-bit security, right? That's what we're trying to do. So how do we do it with quantum secure communications? Is we use some of the properties, for example, entanglement. You can say that there is a pair of photons, and in this particular case, we have shown it with arrows of spin up and spin down. But with photons, we usually use polarization. So we can say it's horizontal polarized light or vertically polarized light. That's what we're doing out here. You have H and V, but H and V are arbitrary. You can also have left diagonal and right diagonal polarization. And these sort of form basis state. The way we do quantum secure communications is split the information into the basis and the value. So in the basis, which is the plus basis, if it is 0, it is horizontal. If it is 1, it is vertical. In the cross basis, if it is 0, it is L, and if it is 1, it is R. And we are sending this information in 2 different halves. So unlike in a classical bit, we just send either a 1 or a 0. So the information and the bit are going together. Whereas here we are sending the information separately and the bit value separately, right? Or we're sending the basis separately and the bit value separately. The other thing we say is that you cannot make a copy of a photon. This is very important because if you send it on one photon, so that one photon can reach one of you. It cannot reach everyone. So if it doesn't reach the receiver, I just ignore it. So let us say my password was 13579, which is not a very secure password, but let us say it was 13579. And I send it on photons, and only the photons 1, 7, and 9 reached the receiver. Then my password is 179. I don't care about 3 and 5. It did not reach the receiver. He got 1, 7, and 9. I got 1, 7, and 9. I'm happy. So China was the first one to actually rile the waters by making this long link between Shanghai and Beijing. And this link between Shanghai and Beijing has a number of secure nodes, the middle shown by these yellow dots, and it also has these little networks at all the main cities along the way. These networks are what I'm calling makans because they're called metro area quantum access networks. And this is what would be their killer, because that is their quantum internet with local access, right? And this allows them to secure their communication. They, of course, have also done satellite communication, which is not something that we're talking about today. So typical quantum key distribution, the way it works is you have 2 parties, Alice and Bob, and they exchange the key over a quantum channel or classical channel that we refer to as a quantum channel because you're using single photons out here. And then you go through a bunch of steps in the classical domain over a classical channel to end up with a secret key, which is then communicated, which then does the encryption and sends the ciphertext over to the decryptor, right? So the actual quantum mechanics is running at about 10% of the entire system. The remaining 90% is all classical hard work, where information theorists and electronics engineers and communication engineers are doing all the rest of this work. Right? There are some things to remember is that if you try to do it in free space, you're usually using 805 nanometers. If you're using optical fibers, you're using 1.55 microns. The wavelengths become important when you talk about technology. And the other thing is that the quantum channel or the keys are running at about 100 kilobits per second, whereas the classical channel is running at 100 gigabits per second. There is something to be said out here because many people will tell you that quantum key distribution is unconditionally secure. It's unconditionally secure only if your engineering is unconditionally superior, right? If your engineering is not, then it is not. So you have unconditionally secure 100 kilobits per second and you're sending encrypted data at 100 gigabits per second. In effect, you're sending using the same password 1 million times. And someone will tell you that that is insecure, right? But that being said, I often ask people, when was the last time you changed your password? You probably haven't changed it for 6 months. It was something like me. I don't change it for years, right? So even if you use it a million times, and we're talking a million times, I know I'm generating it at 100 kilobits per second. So that means I'm generating it, let us say, 100,000 times a second, and I'm reusing it a million times, that means in a few seconds, I'm changing the password, right? So it is still secure, more secure than what we are doing today, which is relying on us to change our passwords. The network itself is going to be comprised of what are called QKD modules, which are inside these QKD nodes, this blue dots with the green circles. They're going to go through some optical switches, and then they're going to relay to another node, and then eventually they're going to talk to the user network, which is shown as a cloud out here, where there's a cryptographic application that is going to transfer information. So there have to be two layers, one layer which is quantum and the other layer which is classical, and they have to learn how to talk to each other. If you talk of the protocols itself, this is one very early protocol. It's called BB84, which was discovered in 1984, which uses the polarization of light. And remember, I described to you how you use either horizontal or vertical polarization, or you use left and right basis, and then you send the photon. At the other end, the receiver, Bob, is going to use either the horizontal, vertical, or the plus basis or the cross basis. And when he makes a measurement, he has a probability. So if you look at this table at the bottom, you will see that if a 0 bit is sent, he chooses the plus bit, he gets a result of 0, although the bit that was sent was a 1 and the photon was in the cross basis. So the bit was 1, the photon is in a cross basis. Bob makes a measurement in the wrong basis and he gets a 0, right? So this photon is lost. On the other hand, you could also make a measurement out here, for example, the bit that was sent was a 0, the photon was along in the cross basis, so it was using this particular 135 degrees. Bob chose the plus basis, and because he chose the plus basis, there's a 50% probability of getting it right, and he gets it right, and he makes a measurement. So in this particular case, he's made a measurement, although he's used the wrong basis, right? So if you go through this kind of truth table, and in fact, it's a little more crazy, you can sit down and go through all of these different cases, you will find that there is a process that is called sifting that allows you to pick when the measurements are made and when we should actually keep them. And that is how you set up your password. So I give you a simple example, 13579, I just use 179. I hadn't added error in there. I send 13579, he gets 189, right? So you also have to correct for that 8 and make it into a 7, right? So there are error correction protocols that happen out there. So you have parameter error estimation, and then you have information reconciliation, and then privacy amplification. All of these also require quantum random number generators, because that is another source of inaccuracy, where the random number generators are repeating themselves. So remember, I'm using my password a million times, but the random numbers are repeating themselves probably at the same frequencies, right? So that's why there is efforts to build quantum random number generators. When you use entanglement, you don't have these kind of problems, because you're going to send one photon this way and one photon this way. And the two photons, if they reach, then you have a secure key. One is a horizontal photon and one is a vertical photon. And you know if this one's horizontal, this one's vertical, and vice versa. So there is no problem doing this. However, you don't even get kilobits per second when you do this. You get about a few bits per second. So it's very hard to set up this in a practical case. The other thing that I pointed out was that telecommunications happens around 1.55 microns in the C band. Actually, there are about 40 channels out there. These 40 channels are used today in our classical communication. If I want to use quantum communications, what I do is I need to pick one of these. I don't need all 40. Turns out that if you pick one, it's not enough, because if I have 4 channels and I pick one, then the crosstalk from the other one, the classical photon from the other one comes into my quantum channel, right? Because the classical photons have enough energy that they leak into my quantum channel, and then my detector says I've got data. So one has to be careful about using some of these things, and there are ways to mitigate that, which we use. This is an example of a classical channel which actually runs about 100-kilometer fiber before you putting an amplifier. This is an erbium doped fiber amplifier. And the reason I'm showing you this is because sometimes people will say, oh, I will do, thousands of kilometers. You can't do thousands of kilometers. There's an amplifier sitting there. It will amplify one photon into 1 million photons. So unless you find a way to bypass this amplifier, you bypass the amplifier and that one photon will never reach even 200 kilometers. So there is a problem with doing this unless you know how to build a quantum repeater. And that is an area of research that people are very actively pursuing, but we haven't yet got a practical quantum repeater. I was telling you about the crosstalk. Typically in classical channels, the isolation between channels is about 50 decibels. 50 decibels is 1 in 10 to the power 5. If you put a quantum channel in the middle, we need 80 decibels. So 1 in 10 to the power 8, right, is the kind of isolation that we need. And this is quite hard to achieve. We can also do things like narrate in a Sagnac loop. This is a Sagnac loop with a periodically poured lithium niobate crystal, and you pump it and you generate photons that you can then send onto different receivers. This is sort of a nice idea because you can generate photons on what is known as the wavelength division multiplexing grid. So this was the WDM grid out here, and you want photons generated on that grid. You can do it using these things called muxes and demuxes, and they will generate photons on particular channels. Right? The issue out here, of course, is that it's a very inefficient system. But if you don't have a very high key rate requirement, you can still do something like this. So we've done some work along these lines, and here is where I have a mode block laser, and then I send it through a Fabry-Perot tunable filter and an erbium doped fiber amplifier, and we end up with sort of a comb line out here. And this comb line is mixed along with a single tunable laser source and sent into a Sagnac loop. This is all fiber based, so it uses a highly nonlinear fiber. And then we see what comes out on the optical spectrum analyzer. Right? So on one side, we are pumping it with this comb with this pump, and the pump is kept separate from the comb and sent into this Sagnac loop. And you'll see out here very nicely that because the comb is already on the ITO grid, I have transferred some energy from the comb lines into the sidebands of the pump. Right? So these photons are all entangled with each other, and they can be used to do this entanglement distribution. Without the tunable, the Fabry-Perot tunable filter, this is the Fabry-Perot tunable filter, the spectrum looked just like this. But by putting that filter in there, I generated these comb lines, and then I transferred it through the Sagnac loop onto the sidebands of the pump. Right? So this is a Chi3 process, which is not commonly used when you use crystals, but in fibers you use a Chi3 nonlinear process. Okay, so we now need to talk a little bit about what is the protocol we use. I gave you one protocol, which is to say polarization. I use either horizontal vertical polarization or 45, 135 degree polarization, plus or cross. Well, because I've not shown you the results of suppressing the pump and then doing a G2 measurement on the Stokes and anti-Stokes peaks. Right? It's not really classical. It cannot be classical because it's nonlinear for sure. Right? Now, the question is, can I show you the results of doing a G2 measurement between the two adjacent sidebands? Right? Third order nonlinearity, right? In a regular crystal like this, you will do a second order nonlinearity of Chi2 crystal, and this will give you spontaneous parametric down conversion. In a Chi3 nonlinearity, you will get sidebands close to the pump. Another easier protocol to use is to use what is called the distributed phase reference. Unlike polarization, so polarization is a problem in fiber that if I bend the fiber, then I lose polarization. So phase is something that we use, and maybe I can very quickly draw it on the board, is if you think of an electromagnetic wave like this, then I add a phase like this. So if this is a 0 bit, then this is a 1 bit or a pi bit, right? So I have a phase reference out there. And a distributed phase reference is very interesting in that I can take the front half of this and let it interfere with the back half of this. And if there is no phase, then I will get constructive interference. If there's a phase of pi, I'll get destructive interference. That constructive and destructive interference will show up either on detector 2 or detector 1, right? So with 2 detectors, I can now tell you whether I had put in a 0 or a pi phase onto my optical beam. It turns out that if you do this fast enough, it takes, the fiber is still there and it destroys phase, but it takes a few milliseconds. But the time duration of these pulses is a few nanoseconds. So it retains its phase information as it goes from transmitter to receiver. You can also improve it by doing something like this, which is using superposition states and saying that if I send a single photon and I send it through the structure where there are delays of t and 2t, it will come out in time bin superposed stream of not really photons, but in superposition states. The photon is either in the first, second, or third time bin. And if there is a phase difference between them, then I will interfere in this particular case, the first and the second one, or the second one and the third one. And I will know that there is a phase difference. So because it will come out on D1 or D2, depending on whether it is constructive or destructive. So one of the things you want to do is to obviously reduce T. You want to send more bits, right? Remember, I was slow. I want to send more of them, so I want to keep reducing T. Well, you could just make T 0, right? And that was one of the things we discovered is why are people struggling so much? Why don't we just make T 0? And then it's even more interesting as a physics because, thought, right? Like a Gedanken experiment, because you're now asking the question, can I take a single photon, shown schematically like a pulse out here, and break it into 3 time bins and allow the leading edge of the photon interfere with its middle part and its trailing edge. So just one photon. I just drew it out here and nobody blinked, right? So I'm going to do this. And what I'm going to show you is that both of these are equivalent. And it's much easier, obviously, to implement this than to implement this. In fact, I can implement this with many more transitions than just 3, right? Because all I have to do is just turn on and off a phase modulator very rapidly. Whereas here I have to keep constructing these delay line experiments, which are harder to do. So phase modulation is basically where you take these sort of 1 nanosecond microwave pulses on and put them on a 3 nanosecond optical pulse. And then you can transfer 0, pi, 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 pi 0 or 0, 0 on that. And you'll see that you can, whether you run both the type A experiment or the type B experiment, you're actually supposed to get everything sitting out here and out here, which is what you end up doing. In fact, you might end up doing better in type B than in type A, right? So it turned out that doing the type B was, I mean, it came to us by happenstance because I kept trying to reduce T. And I found it harder and harder until I just said, I mean, why am I struggling so hard, right? And it turns out that you can do better with this, and you can also put it on a photonic integrated circuit. This is hard to do on a photonic integrated circuit because you can't put 1 nanosecond delay lines on photonic integrated circuits. The other protocol is a coherent one-way protocol, which uses either a vacuum state or a photon or a coherent state. So a vacuum state or a coherent state as bit 0, or a coherent state and a vacuum state as bit 1, and a coherent state as a decoy state. And this relies again on understanding whether there's an eavesdropper by having a separate monitoring line and doing an interference between 2 coherent states. And if there's an eavesdropper, then it destroys this interference. So I won't spend too much time on that, except to say that you can run these coherent one-way protocols up to about 150 kilometers. But you'll notice that the key rate just keeps on dropping. So if you try to go much longer, you just won't have a key for a long And you need some picosecond resolution to be able to see the logic 0, which is a coherent state and vacuum state, or the logic 1, which is vacuum state and a coherent state. Right? And finally, the last one is this new idea that we've had of doing differential phase shift measurement device independent quantum key distribution. What is measurement device independence? It assumes that the guy sitting in the middle is insecure. Okay, I don't really care. He can have all the information because he has the detectors. So there was this idea that the measurement device, which is a single photon detector, is insecure. You're buying it from somewhere in the world market, and so it is insecure. But can we come up with a protocol that says that even in that case, we can have a secret key between Alice and Bob, and you'll notice immediately, of course, that you've doubled the length of your system, right? Because earlier you had about 100 or 150 kilometers, now you can do 300. And that's what is shown out here, is that you can do it, but this becomes 25, and then if you double it, it becomes 50. So you really don't get the benefits, but you do have the benefit that if you have a eavesdropper in the center, in this particular case, the measurement device, you still can set up a secure key. Right? So these are all the new ideas. And the last one that I want to throw out there is this idea of timing, because these single photon detectors are usually gated by an electronic pulse, and unless these two match, you don't get an output signal. When they match, you get an output signal. But this photon need not necessarily be at the same width of this electronic pulse. Electronic pulses are much slower. This photon could be 10 picoseconds. So this photon could arrive at different times within this electronic pulse. And depending on when it arrives, you actually have higher or lower efficiencies. So again, we ran some of those experiments, and you can see that we estimate that the photon is arriving anywhere within about 250 picoseconds within our electronic gate, and the electronic gate is 2 nanoseconds. So it is important to understand things like this. Should I send it such that the photon arrives at the start, or should I send it so that the photon arrives at the end? And it turned out it's not very obvious how to think of these things, but it is better that the photon arrives at the end of the gate than at the start. What happens is, if the photon arrives at the start, then there's a lot of, in this region, there's a lot of buildup of avalanche electrons, which are then left over, and they will be emitted in this gate pulse as a false detection, right? So it's better that you do this, and then you have a lower error rate. Right? So very interesting. So coming back to our main idea is, this is our national knowledge network connecting all the different metros. How do we want to secure this communication, right? And these are our optical networks. You have the access networks and the metro area networks. I showed you how we've run some experiments to see if we can safeguard this, but really we have to also do the long term, right? So the metro area quantum access network for us is a network that is set up between IIT Madras Research Park, and the Society for Electronic Transaction Security. It also has, at the research park, it also has ERNET, which is a person in the middle. There is Bharat Electronics also out there. And then eventually we hope to get to the National Informatics Center, which will connect us to the National Knowledge Network. These are what our boxes would look like. And, this is a very small area, right? Maybe about 15 kilometers or something like that, right? From here to here, from SETS to NIC is about 15 kilometers. Metro areas are usually 50 kilometers max. Boxes that look like this is what we need. These are 19-inch rack mountable boxes. It's called a 3U box because it's 3 inches. No, actually not 3 inches, 9 inches. And it has a bunch of optics, and it has a bunch of electronics. And this electronics is also transferring clock synchronization over these modules called the White Rabbit Master and the White Rabbit Slave. And we synchronize the two boxes, and then we do time stamping in order to figure out when the photon is actually arriving. What I didn't tell you when I gave you my example of 13579 and nobody asked was Bob received 179. Inherent in that discussion was that there was a timing involved. I mean, I was doing 13579. Bob received 179. That means he knew he is receiving it in the fourth and the fifth time bin. So you need the time stamping. Otherwise, if he just gets 179 and I send 13579, then my 135 and his 179 will not match, right? So the timing is very important. This is what the electronic optical assembly would look like. This is what the electronic assembly below that would look like. It's all indigenous. Well, this is becoming indigenous because we are building this board, but this board is already built. Right? And this is the Google Map version of that other picture for Makan. So you have IIT Madras here, the research park, and sets out here. And we have managed picosecond synchronized clock distribution over the optical fiber. There are other people who have done similar demonstrations. CDOT has done a demonstration in Delhi. They have also got a setup operational in IIT Noida for a while. In Delhi, there is between Sanchar Bhavan and the NIC headquarters. So understand why we are all trying to get to NIC is because all our institutions are connected to the National Informatics Network. IIT Delhi has done another demonstration that goes from Prayagraj to Vindhyachal over 100 kilometers. This was done along with the DRDO's, IIT Delhi and DRDO's team. So they have also been able to do this. Why am I telling you these things? Is because everybody is able to do this. We need to have a way for everything to work together. It's not that, only one person has to do all the work. So to make it all work together, there is a what we call a quantum software defined network framework called Disruptive that we have started building. You can see the nodes that are active, and then when any other node becomes active, you can set up a key between two nodes, right? So that's how the software works. And let us say these are my boxes in blue, the Makan nodes, and then this is the CDOT boxes. So there has got to be a secure relay between these two boxes, and then there's an encryption app out here. So there is a need to understand that there is a controller that is talking to all these things and a key management layer that is handling a lot of this, right? So there's a lot of work that is done in trying to understand how to build these networks together. And then there are some not so simple problems. Most of you do not realize this, but you can tap into your optical fiber very easily. You open the box, you'll see it leaking out, and then you just look at it, right? It turns out that when we opened it, it is supposed to look like this, but it looks like this because the box is not sealed correctly. There's dirt inside it, right? All kinds of things. This was also very interesting that we have two fibers. And I was talking to you about that those 40 wavelengths on one fiber. Assumption is that there's crosstalk, I can just put another fiber and there's no crosstalk. But in this particular case, the photon, the classical information was from here was being picked up on my quantum channel out here. Two separate fibers, right? So we actually had to go in and put tape on top of it in order to reduce it. And you can see that on the classical channel, I was sending my clock, and my quantum channel, which had my single photon detectors, I'm picking up the same signal. Right? So it's so easy to tap into fiber now that is still scary. So the first test bed for Kila is actually this Chennai to Bangalore link. It's supposed to be about 350 kilometers, but if you go through the fiber, it's actually 550 kilometers. And so we are planning this particular link out, and hopefully we will have some of the chips ready for it. The chips are being taped out. They should come to us by December and packaged it by March. So sometime next year, we are hoping we'll be able to start building out this network. And then, of course, you go back to the full main goal of our fort. Kila is supposed to do the test bed from Chennai to Bangalore and then go from Bangalore to Hyderabad to Bhopal, Indore to Delhi, right? So that's about 2,200 kilometers, and Chennai, Bangalore is only 350 kilometers, but if you look at the actual fiber, it's 550 kilometers, right? So there's a lot of work around this that we're pushing under this National Quantum Mission. In India, yes. It will be, yes. It will be. right? More than that, it's not a lab demonstration. It's actually field deployable, right? Which means everywhere where my fiber is leaking, I have to go and send someone to put tape on it and things like that. So the point-to-point links will go to about 300 kilometers if you have a very low rate. If you can do shorter links, then you'll get a higher fee, right? But that is our national quantum mission on the terrestrial quantum communication over 2,000 kilometers. What we are planning to do. Okay, so I'm out of time. This is our quantum communication team. It's a mix of theorists and experimentalists from physics, electrical engineering. Not really for quantum communication. We don't bring the biotechnologists, chemistry, and the metallurgists in there, but at least the physics and the electrical engineering, and there's a computer scientist also involved in doing some of this. And the rest of them are project staff and masters and PhD students. And the collaboration itself, I think one of the successes of the project was because we had a collaboration between many organizations, IIT Madras, SETS, CDAC, Bangalore, and Trivandrum, and ERNET. As you start scaling up, these collaborations become more important. As you see that SETS does a lot of the shifting, error correction, and privacy amplification. I did not talk to you about post-quantum cryptography, but when the link fails and you still want to send your password, your next best bet is to use something called post-quantum cryptography. And that is inbuilt into our systems today so that we can still guarantee quality of service to the end user. Right? All right. And of course, the funding agencies, we started a lot of this work very early on, and then we stopped for many years because nobody was interested. And then the quantum computers came, and then everybody started getting interested. So the quantum computers have kicked off this particular thread. And we've got many demonstrations, the latest one being Bakan, and then finally we're going to head towards Kila. We've also got this incubated company that has now got an order for about 50 units from the Indian Army. Right? So there is a lot of interest from the defense and other establishments hoping to secure our networks. So let me stop here and take questions. Yeah, why don't you check the questions online?
Is there any questions from the online audience? Am I audible? Is there any YouTube any questions? Live chats. Live chats. Okay, so now any questions? So you can start.
Doesn't have questions. We have questions. Yeah.
Anil,
Yes.
are our undergraduate students contributing to this program? Means what is the level of their participation?
I'm just answering a question out here. We're just getting started with the Q&A here. Sorry, what was your?
So I have to do it.
Yeah. So my question is, already we have a lot of fiber network, the existing. Then how we can use them? Like, yeah.
What I was showing you about the existing, the ITU grid, the C-band and the ITU grid. The reason we are doing that is because it's existing fiber. Even the Chennai-Bangalore link, we are trying to do on existing fiber. So as far as possible, we are using existing fiber. The Chennai-Bangalore link is dark fiber. It is not used. So I don't have this problem of crosstalk from the classical channel. Bangalore to Delhi is going to be used fiber. And I'm going to get, so the idea for me is I'm going to use 4 channels. If you remember in the early part of the talk, I said that the quantum communication is only about 10% of the work and the rest of it is classical. If I get 4 channels on an existing fiber, I will put my quantum channel in the middle out here on my ring, my thumb finger. And then I'll put the classical channel here and I'll keep these two as guard bands. So these two guard bands mean that classical will not leak over either from here or from here, right? And then we have to do some aggressive filtering to make sure that we get 80 decibels of isolation between the classical and the quantum. If you can do that, and the C dot demonstrations have done that, we have also done that. So it seems like it is possible. Any other questions?
Okay, so I have a non-technical question. It appears the one implementations and other things, for example, this Bangalore Chennai network. Yeah, so it's like for me, it's like a full-fledged company kind of one big thing which is doing from complete quantum cryptographical network from Chennai to Bangalore. I'm a humble theoretician. It appears to me a big thing in the sense that how are you managing it from the experimental lab, or is it a separate thing? It's kind of.
Well, it's a very valid question, and that's what I keep telling everybody, that academics need to understand the scope of what we are aiming for, right? I would not be able to do this unless I had the support of CDAC. CDAC has sufficient staff that they could put onto this in order to building a lot of the hardware and the firmware. Sets has staff that can do a lot of the thing. So I can do small pieces here and there. My specialty is to do the quantum optics, understand the protocol, learn how to do the characterization. But it's really not to build these things. So this is where the collaborations become absolutely critical. There is no way that I am going to do a link from Bangalore to Delhi. I mean, if something breaks in the middle of the night, I am not going to go and fix it. There has to be other organizations, and we're hoping that organization like EarnNet that handle a lot of this on a regular basis will pick up that slack, right? So academics have their role to play in terms of technology development, but in terms of deployment, maintenance, field characterization, we do have to rely on either government labs or industry come in and do this. So that's how it is done. Any other question? Not, there are no other questions online either, then.
Is there any questions from the online audience? Yeah, so if not, let me, is there any question? Yeah.
We can show
No,
in chat.
in chat. I thought.
Capacity building workshops, or can there be capacity building workshops for science students across the country? The answer is absolutely yes. We continue to do this all the time. So yeah, if people are interested in something like this, please, this talk itself is a version of capacity building, but if you have ideas on how we want to pursue this, please do reach out to us and we'll be happy to sort of build capacity. I'm not sure what we'll do once we have the capacity though. I think it's interesting, but after a while, if it becomes, a lot of it, as I said, again, is engineering, right? I think there was one slide that I did not get to, but I flashed very briefly.
In this regard, I feel that the undergraduate students from across the country are left out because there is no course during their undergraduate degrees. In that case, it has to be something has to be done because they can't be left out. All the things are being done in IITs and ICERs. So I think that every science student should also be aware of these things. It is not a field which can be taken up by anyone unless or until there is a pre-knowledge required in that, and that kind of thing I think is being missed out. This is my personal
I agree
opinion.
with you. We do our best in terms of outreach. And we interact a lot with a lot of the local colleges around Chennai and maybe southern parts of Tamil Nadu. It's also something that no individual institute can take up. So we do a lot of training through the online medium for teachers and other people who are interested, and hope that the word will spread. That being said, I would like to correct this notion that it has to be science students. If you look at my quote out there, it says rely on engineering. You believe in your physics, but rely on engineering, right? It's absolutely critical that the engineering students understand that it is not beyond their reach, because about 90% of the work is engineering. It's not science. I mean, once you figure out you have a photon with a polarization or a photon with a phase, you're done with the physics. After that, you're busy engineering everything. So it's important that the engineering students step in along with the science students to make these things work, because a lot of it is understanding information theory, cryptography. It's not only about quantum mechanics. I think that's the realization. Actually, that's a realization I had when I first joined IIT Madras, because I realized that it's nice to say that you work on lasers, but you need electronics to turn it on and off. So I had to teach myself the electronics at that point. Right? So I think high-speed electronics is just name of the game today. But I think the point taken is very true. If you do have ideas on how to improve our public dissemination of knowledge, we are happy to listen. Any other questions, comments?
Yeah, Anil, first of all, I would like to congratulate you for the wonderful program you're leading. It's a great thing for India, and great admiration to you and your colleagues. And the question that I was bringing up a little earlier was in line with what Dr. Vandana Luthra also raised, but it was a subset of that question. I just wanted to know if undergraduate students at IIT Madras are contributing significantly to this program.
Not significantly, but they contribute. I think a lot of the undergraduate programs contribute a lot to our quantum computing initiatives. They don't contribute quite as much to the quantum communications. But that being said, it's not a null set. So there are every year we get about 1 or 2 undergraduate students who are interested in this and who pick up projects around quantum communications.
Very nice. Arvind? Arvinda?
Yeah, I think, thank you. Okay, so let me thank Professor Anil Prabhakar for a wonderful talk, and especially for a physicist. It appears really engineering stuff. Okay, so thank you. I thank everyone for attending this talk. Thank you all.
Thank you, Anil. Thank you very much for coming. It has been a wonderful treat. Thank you. Goodbye, everybody.
Anil?